Hello, everybody. How are you? Pretty good. Zoomers? Tired? Good. I'm good. It's Friday. It's good news. Okay, so I have a few announcements to make before we get into everything bogging off. Okay, so I wanted to bring up, and maybe I got to share the screen with the Zoom folks. I wanted to bring up a seminar that's going on today that I would strongly advise you go to if you can. And that's from Jen Heemstra from Emory. Anyone ever heard of Jen Heemstra? Maybe, no, yes. Very inspirational individual in the field of sort of post translational modifications, sort of applicable to what we're talking about here in MedChem. It is extraordinarily difficult to get her to come out and give a talk because she's so popular. I think she spends most of her life traveling because everyone wants her to come speak at their school. So I would take the opportunity to go to the seminar if you can. Jen, yeah, she's at Emory. Fantastic work, really, really cool, and has a little bit of overlap with MedChem. It's going on today at 2:30 in the Biodesign Auditorium. You can do that, or you can go to the Zoom link down here. I'll post this after class. You guys can go. I'm willing to offer up 10 points extra credit if you go to it, and then you give me 2 paragraphs, one paragraph being sort of summary of what you talked about, and then a paragraph discussing sort of what you learned from it, maybe how it relates to MedChem. I'll put some instructions and guidance about that afterwards, but I usually do this pretty often throughout the semester. If you guys go to seminars, I think are pretty interesting. I'll usually toss you 10 points. It's worth going. Do you guys go to seminars ever? Yeah, good. Yeah, I mean, it's a really good thing. And biodesign usually has some really good talks that sort of relate to what we're talking about. So I would definitely do that if you can get out there. I'm just going to stop share just for a second. And then get an email link. I'll send you guys the flyer right over the announcements of Canvas. A couple other things to note. Your quiz 1 grades, I promise, will be there at the end of the by the end of the weekend. Exam 1, we've started grading. They're looking pretty good so far. I would anticipate us having those to you by Wednesday of next week ish. Okay. We'll be discussing the honors project next Monday. We'll have that obviously recorded. If you're going to miss that, and you want some clarification, you can meet with me sort of one-on-one, especially if you plan on doing it. And then, yeah, if for some reason you have not taken the exam, that's concerning. So please reach out to me and let's talk about why or why not, and maybe get that squared away. I want to figure out what's going on. I received a couple emails saying I forgot there was an exam. Don't forget you have an exam. Also, the exam thing, if you're on Zoom, please get it to me within the half an hour. Some of you were a couple minutes late, that's okay. But like when you're a good 8 hours late, that's not good. That makes sense, right? So next time it's going to be a point off per minute that it's late. Seems reasonable. I know. Oh, cool. Great. Okay. Are there any general questions before we get started? I think there's a question here. Yeah, so they're not going to record it. So you'll have more opportunities throughout the semester. I usually cap it at, I think, 5. So you'll be able to get 50-ish points of extra credit throughout. So I would say plan on attending the next one. Cool. You get so stoked to finish up phase 1, phase 2 transformations. Yeah, Kyle. Okay. So let me bring this up. Okay, so last time we were talking a bit about pharmacokinetics, right? I want to get over to the slide that we were at. Give me 1 second. Hopefully, it lets me escape. Slide 28. And I wanted to bump back just a slide or two from where we were at. Right. So here we are. We're probably maybe 1 or 2 slides back from where we were at last time. So something I want you guys to notice, and you'll get sort of the hang of this as we go through the material is so last time we talked about sort of P450s being able to do those sort of oxidation events. And so, for example, in this case of lidocaine, you have the oxidation event in sort of an activated position, right? So those positions that are right next to nitrogens or phenyl groups, et cetera. And I would make a sheet of that earlier than later, and sort of getting to practice these. And then at that point, right? So this is it'll kind of go from there to sort of will be sort of removal of water ultimately, and then it can cyclize, for example. So this will be sort of the types of things of problems that you'll be faced with as you move along, but you guys will get plenty of practice before you head into exam 2. These types of mechanisms, right, that show sort of the iron center, right, the full-blown mechanism of the P450s. You're not going to have to know. It's there for your reference, but this is a good example of direct sort of oxidation of nitrogen, for example. Again, right, this is another example of this being the oxidation of the carbon right next to the nitrogen. And so, I would think I would take a few minutes and sort of look between these and sort of get a feel for what's happening. But these are probably these single electron type mechanisms are too I would say high level for the course that we need to know. Right, so metabolic activation, right, can also occur for primary and secondary aromatic amines, right? So you can so you start with sort of this aniline here, this aromatic amine, and that gets directly hydroxylated, as you saw in previous slide. And then ultimately we'll talk about what these X's are, but those can get attached to the molecule, and ultimately they function as a good leaving group. And so once you have a good leaving group on there, right, that can leave, generating sort of this nitrogen plus, very similar to the carbocation formation. And then at that point you can go ahead and follow the arrows, and you'll actually get sort of attachment to what would be sort of a macromolecular target, like a protein, for example. And at that point, right, then you can go through this process. You guys should be pretty familiar with that. What is it? Good. That's what I'm talking about. There's some enthusiasm. Okay. I know you're tired. Okay. I know it's like, do you really want to say that out loud? Anyway, bioactivation of acetaminophen, right, looks sort of very, very similar, right? This is the type of, this outlines essentially a very similar type of mechanism from the previous slide, but again, these ones, actually I would say maybe specifically the ones that come from the Silverman book. Those are not going to be ones you need to know, and you could probably recognize those, right? They're not blue, so I wouldn't worry too much about them, but just sort of get a feel for what's happening for your own interests. Right, those oxidations from cytochrome P450s can also happen on sulfur, right? So you have sort of you can get sort of direct sort of sulfur bonding. You can also sort of go from structures like this directly to the ketone. You're not going to be faced with the second one on the left at all in the course. I think what I would maybe focus on in this one is sort of just direct sort of oxidation from sulfur. So you'll start with like R, S, R, and then when it comes in presence of P450, it just becomes so that S gets an oxygen attached to it. That's as far as you're gonna need to know. Same thing can happen right with phosphorus compounds, right? So they're capable of oxidizing not only sort of activated positions, but also directly on heteroatoms. It will not happen on oxygen, by the way. What that mechanism look like, again, is sort of outlined in this slide. And again, that's for your own information. And it goes through sort of oxidation through the heme complex. This example comes up, sort of a whole bunch of times, right? You guys have seen this a couple times. This tianilic acid. Now we're maybe to the point where I would say that we could start thinking about doing a mechanism that looks like this. I'd say it's about plausible to be able to do. So what I would say is, you start with the tianilic acid. You know that in the presence of a P450, you'll actually probably start with sort of 8.92 here in the top left. Then I'll give you sort of 8.93, and I'll say, okay, you got to rationalize a way in which that happened right through metabolic processes. And so, one of the things that you have to do is think about, you need to make this thing, this sulfur a better electrophile, sulfur containing ring. At that point, right, you're able to go ahead, you do the oxidation, and now you have this S plus. It's going to make it more electrophilic. And then whether it be your macromolecular target or let's say this sulfide here is going to be able to come in, attack, and sort of attach to your molecule. I'd spend a few minutes looking at these as we go along. This is a good time now to spend half an hour, even a day, right, going through sort of the arrow pushing, so you get a real feel for what those types of problems will feel like. It becomes sort of second nature to you. You'll start to see sort of the connections across the board as we get into sort of more advanced type problems. So flavin containing monooxygenases, those ones are going to be very, actually I think pretty much every time we're going to be just doing oxidations onto a heteroatom. So they're very common in sort of doing N oxidations. Those are abbreviated usually just like FMOs. And I'll give you some guidance on that as we go along. But here's some good examples of what they're able to do. And as you can see, right, they do things that are very similar to a P450. So oftentimes people will use a P450 or a flavin monooxygenase interchangeably on an exam, for example. Whatever you can pick your favorite oxidizing enzyme. And then right, they can do these sulfide bond formations too, very similar to the P450s. Right, and then again, you have some more N oxidations and sulfur oxidations on the right side. Right, so dehydrogenases and monoamine oxidases are also going to be in phase one. Remember, in phase one, you're trying to take something that's pretty non-polar and make it a little more polar as sort of a signal to start either actually processing it or getting rid of it. And so a couple that'll come into play are going to be the alcohol dehydrogenases. The reverse of that would be a keto reductase. Right, so keto reductases reduce the ketone, and alcohol dehydrogenases oxidize the alcohol, for example. You also have aldehyde dehydrogenases that when they're doing the dehydrogenation, right, they're doing an oxidation. So for example, right, it takes this aldehyde to the corresponding carboxylic acid. Yeah, in sort of analogy to this primary alcohol one, right? You can also start with secondary alcohols and alcohol dehydrogenase and come in and do the oxidation from the secondary alcohol to the ketone. And then finally, you have these monoamine oxidases, and usually those are direct conversions from amines to aldehydes. Yeah, so the alcohol dehydrogenase, not particularly common. You also see actually a lot of sort of conjugate additions. So we talked about in sort of a little bit of the review as we sort of transition from exam 1 to now material for exam 2, that's sort of the most electrophilic position in sort of those 1,4 the alpha beta unsaturated compounds is in the 4 position, right? So what these usually do is they deliver a hydride instead of like a normal nucleophile. They deliver a hydride, so just H minus to that position. So you can imagine if you delivered the hydride to this position here, these electrons will come up, it'll form the enolate, and that enolate will just then be protonated afterwards. Right. So this is what I was sort of talking about. So these alcohol dehydrogenases again, right? The reason why they say these are not common is they usually aren't thought to do a reduction. When you're thinking about it in the reduction direction, you usually think about them as reductases. So they're literally ketone or aldehyde reductases, for example. Alkyl halides can also be reduced. And so again, your nucleophile in that case is very similar to an SN2, only your nucleophile is H minus. Right, so these phase 1 reductions actually can also occur by P450s. So right, they're a pretty versatile enzyme. So you can go ahead and if you start with these N oxides that you formed from even, let's say, a separate P450, it can also be reduced back down to the imine via P450 as well. Nitro groups can also be reduced. So on an exam, if you go from a nitro group to an NH2, you can just say P450 and we'll buy that. Azo compounds can also get reduced to sort of the hydrazine here. And then it can be reduced again to the corresponding sort of anilines in this case. So the 2 sort of aromatic amines. You can also have reduction of disulfide bonds to generate the corresponding diol, or sorry, the thiols rather. And then you can have reductions at heteroatom centers. So you can go from, for example, the sulfoxide that you see down here to the corresponding sulfide. What those mechanisms look like are sort of, one example would be sort of the nitro reduction, which you see up in the top. Again, isn't that something you're going to have to really focus on, but I would take some time and sort of try to understand the arrows a little bit, just so, just getting any sort of practice with that is going to be really helpful. Something like this is sort of a nice example of having to do a transformation and then see, what's going to happen after it, right? So you have this nitrofurazone, and you can get reduction by a P450 from the nitro group to sort of this sort of N oxide species here. And you can go through, right, another reduction to get to the corresponding amine. Then at that point, the amine can fall apart and sort of open up this 5-membered ring. This is probably on the maybe super challenging end of things that you would see. You're likely not going to see something like this. Azo group reduction, right? This is an example that we saw a couple of slides ago, right? Again, so you have this sort of a single electron sort of type process that goes on that ultimately generates the hydrazine. And then finally, you get, another reduction that generates the corresponding aromatic amines. And just this is shown in sort of this example here, right, by reductive metabolism of sulfalazine. And so what you start with is this nitrogen species here, right? And ultimately what that does is it goes through two reductions, and it just splits the nitrogen into two corresponding NH2s. Those reductive halogenation reactions, sort of what we're talking about from before, right? You can either have sort of that sort of hydride delivery to the alkyl halide via, sort of like keto reductases, for example, or you can have sort of the single electron type process with P450s, and sort of this outlines it here, but ultimately you have sort of a single electron reduction. You get to the radical here, and then it can go a couple of different ways. It can get reduced again to generate the anion, and then it can do sort of elimination type pathways to generate alkenes, or alternatively, right, it escapes from the enzyme and you generate the radical, and that radical can either abstract an H or hydrogen from another molecule, or it gets quenched as a carbocation. Again, this isn't going to be, particularly useful information for you at the moment, but just so you're aware. Yeah, esterases and peptidases are absolutely going to be super important, and they've already been important in the course, right? If you guys did, you're studying for exam 1, right? You've seen sort of, these come into play. Definitely knowing the difference, right, between an esterase and a peptidase is important, right? The esterase hydrolyze or add water to esters, and then alternatively peptidases, they hydrolyze or add water to amides. Oftentimes that's usually what breaks up peptides, for example. Okay, so now we get into phase 2. So now you have sort of the situation where now you've installed sort of a more polar group onto the molecule, and now you really want sort of a boost, right, and sort of some sort of signal that's going to indicate, okay, let's get rid of it. So what you do is you attach something even more polar to that polar group, and so a really great option for that would be to attach one of these glucuronyl groups to it, and that's a sugar essentially. So usually you'll start with an alcohol, so for example, phenols. So alcohol is attached right to the phenyl groups, normal alcohol or carboxylic acid, and it'll actually transfer this enzyme glucuronyl transferase will put a sugar onto that, right, which makes it much more polar. It's got all these polar groups on the sugar. And at that point, it's ready for excretion. This is just to show you a little bit of the mechanism. Not particularly important for you to know, but you start with UTP, generates PPI, and you get to sort of this species here that's going to give you, that's going to sort of deliver your glucuronyl group via help with UDP G dehydrogenase. What that enzyme actually does is it takes this this alcohol up here to the corresponding carboxylic acid, and that sort of signals that glucuronyl transferase should pick it up and transfer the sugar to the alcohol, for example. And so ultimately, you bring in sort of your nucleophile. This RXH is sort of the R, let's say OH, and you can attach the sugar to it. What types of groups are affected by glucuronylation? Sort of the whole host of ones that sort of have a free H, right? So amides, hydroxylamines, alphanamides, amines also can be, tertiary amines, although not as common, and then thiols, right, would be prime candidates for those. Right. And then you have a sort of a whole other class, right? So once again, you're going to install another polar group onto your already polar group, your alcohol. And so, another class would be the sulfotransferases, which are going to put a sulfate group onto the alcohol, right? So you start with your alcohol, use sulfotransferase, and you generate the sulfate conjugate of that. It can also happen with amines. So you can go ahead and sulfonylate your amine. Mechanistically, it's sort of outlined here. Right? You start by putting a sulfate onto, or you exchange sort of a diphosphate for a sulfate on ATP, and then ultimately you go ahead and very similar to the glucuronol transferase, you have sort of a signaling by functionalization in order for sulfonyltransferase to use it, and that's through this APS phosphokinase that's going to take this alcohol in the bottom left here over to the corresponding phosphate, and that's then going to bind to sulfonyltransferase and deliver the sulfate group. Yeah, so where does this come into play? This is exactly sort of what we were talking about a few slides ago, right? So where you first do, let's say this is sort of what it would look on like on an exam. Might show you something like this, and you'll say, okay, P450 comes in and does this hydroxylation. Okay, but that hydroxyl group is not a particularly good leaving group. So you have to make it a good leaving group, and the way you do that is going to be to install a sulfate group, for example. And once you get to here, you now have a pretty good leaving group. And so if you do sort of the so the resonance type arrows affiliated with that, you can make that sulfate leave. And now, right, this is sort of would sort of be analogous to an alpha beta unsaturated compound, right? So if you can imagine this group up here, right, the nitrogen being sort of the 1 position, right? And then you have 2, 3, 4. So it does that sort of conjugate addition, very similar to the Michael addition. And then you get to this intermediate in the bottom right, and then finally tautomerization. It's good. It's just making sure everyone's awake. I know I get it. Okay. So right. So another option, right? This is sort of falls right into the same camp. Right? You're trying to put another sort of polar group onto the molecule, and so you just start with the carboxylic acid with acetyl-CoA or acyl-CoA synthetase. You can put sort of the AMP group on it. You don't really need to know necessarily these steps, but then this sort of CoA unit comes in, attaches here, and then ultimately you use amino acid and acyltransferase to put sort of an amine on it. So ultimately you generate an amide. But remember, the other thing to keep in mind is what would be sort of the relative sort of polarities between the carboxylic acid and the amide wouldn't be that great. But usually these amides that are put on, right, is sort of an amino acid, right? So it also has sort of the carboxylic acid affiliated with it too. So you've now turned a carboxylic acid into sort of into an amide carboxylic acid unit. Mechanism here, right? So this also is relying on ATP. And then, again, you have this CoA come in, and that basically makes this acyl group a good leaving group. So the amine can come in with assistance of the amino acid and transferase, put the amide on, and then it's ready for excretion. So this slide, I would say, is a really good example of something you might see on an exam. So you have this situation where you start with this 8.153 here, right? P450 comes in, and if you look at the difference between these two, right, it's lost a methyl group. So P450 comes in, hydroxylates one of the methyl groups, and that falls apart, right? The nitrogen gathers an H, and then the P450 comes in again, does the same thing. Okay, and at that point, right, then you can have another P450 come in and do sort of that deamination via the same mechanism. So it's like those three steps are all the same thing. There's hydroxylation in the alpha position, and then sort of departure of the or sort of breakdown of the intermediate. At that point, then you have the aldehyde dehydrogenase come in, and you could take that up to the carboxylic acid. And then ultimately, right, it's got to get ready for excretion, right? So you're going to go ahead and use glycine and acyltransferase to get to 8.155. I know you're probably like shaking your head, being like, "How in the world am I going to be able to answer those problems later?" You're going to have so much practice with them, so don't worry. This is where it becomes fun. I know it's hard to convince you that on Friday, but this is the good stuff. Okay. So then you have glutathione is another example of sort of those phase 2 trait transformations. And so to start you off a little easy in that section, if this is the group you want to add, this glutathione, you can start with an alkyl halide, for example, and it's just going to do an SN2 attack on that, and you're going to generate the glutathione conjugate. At that point, then you have metabolism of that intermediate, usually via peptidases. So those peptidases are going to cleave the amide bonds, right? And then you're going to have acylation or acetylation rather, right? So this is sort of a great sort of combo slide, right? That sort of pulls sort of a lot of concepts from this section together. So I would star this one if you have the ability to do so. Yeah, so this goes back to sort of a couple of classes ago, we said, okay, P450s can do these direct oxidations onto phenyl groups, right? And they generate these sort of arine oxides. Okay, so we talked before about sort of there being sort of these hydrolases that come in, epoxide hydrolases, and you generate, let's say, the diol. But glutathione can do the same sort of thing. So you end up with the alcohol and the sort of the glutathione conjugate as the two substituents at the end. Once again, right, the 4 position is most electrophilic on these alpha beta unsaturated compounds. So you can have glutathione addition to there. This one in the top right is very similar to the one on the left. And then you can also have these add to sort of a sulfate group also, making a leaving group leave. So in this case, it'd be methoxide. Yeah, so a few examples. You guys saw, I think, busulfan was on your exam, right? I know, it's giving you memories. Okay, so this is a really good example, right? Glutathione can attack that. And then I can attack sort of again to make sort of these sort of cyclic structures here. Or in the case of, let's say nitroglycerin, you can go ahead and attach a glutathione group, and that's going to sort of facilitate sort of this disulfide bond formation, for example. Yeah, so yeah. Yeah, just in the book, sorry, in the Silverman book, all the structures have like names, and they're numbered, so that's where those are all coming from. Okay. Back in the day, you guys learned SNAR. You guys know what that means? It's like an SN2, but on an aromatic. So you add something in, electrons go up, come back down, and then something leaves. So I'll put together a slide on that. But glutathione is really good at sort of doing this sort of SNAR process. And so it looks sort of like this, right? The glutathione will come in, sort of in, right? This looks like sort of that 1,4 type of addition we've seen before. Electrons go up into the nitro group, come back down, and it makes this sulfide leave. So ultimately, it's replaced this sort of base down here with the glutathione unit. Right. So there's a lot of good examples actually in the Silverman book of this, and sort of the real life type applications. And so what you have in this case is if you started with morphine, right, P450 can oxidize that up to what would be this 8.163 here, and at that point you now have a Michael acceptor for glutathione. Alternatively, you can also have sort of this oxidation event to get you're not going to see this, but sort of a more extended system seen here, and you can get sort of an addition that's sort of a little more complex to understand, but I'm not gonna give that to you. Metabolism of glutathione conjugates yeah, right. So this goes through sort of this is a much more complicated mechanism, I would say. And in particular, this is not one you need to know. What you basically you're just going to have to know is how you put the glutathione conjugate on, and then from that point you're not going to have to know any of its metabolism. But this is here for your own information. Yeah. So phase 2 reactions, they increase polarity, right? So methylation and acylation reactions actually, right, they decrease polarity, but they are phase 2 transformations. So again, you've already put a group on in phase 1. Usually the target group to think about is sort of alcohol, and at that point you go through sort of a phase 2 to sort of slightly modify the molecule for excretion. So so some other examples of phase 2 transformations are going to be in these methyl transferases. They don't do anything special other than deliver a methyl, and that's all you're going to have to know about them. They could do that to nitrogens. They can do it to sulfurs. They can also methylate pyridines to these sort of pyridine salts here, and they can also directly methylate in oxygen. So there's sort of O methylases, N methylases, S methylases, for example, and I think that's the entire group of them. Then you have acyl transferases, right? These are again not doing anything particularly special other than delivering an acyl group to the molecule. So these N-acyl transferases are they're putting an acyl group onto the molecule. Are we familiar with what an acyl group is? Yeah, it's like like a methylated ketone. So it's usually like the group that you start with, and then sort of ketone, and then a methyl, an acyl group. I think of it as like putting acetic acid onto it, if that helps. Right, general mechanism for these, you're not going to have to know, but here it is for your information. Yeah, this is great. Oh, this slide, man, you want to wake up to this slide. This is like prime candidate for an exam question. I'm going to give you molecules, and I'm going to say, give me 5 or 6 locations that you think are going to be most prone to metabolic degradation or modification. And then sort of the next level, which we'll talk about sort of in the coming weeks, is going to be, okay, so design something in which we could prevent that from happening. And that's where it gets to be really cool. You guys don't have those technologies yet in your brain yet, so don't worry about that. But right now, I would get a real good feel. This is a good time. It's worth, I don't know if you guys ever read on Saturdays or study or something. Yeah, all right. I usually wake up with coffee and just, do a couple hours just like flipping through. It's worth doing that now and understanding sort of the metabolic processes now before you get into sort of the next stage. So I would say to sort of budget in some time to look into MedChem, because I would say the second exam will get a little more difficult. It requires a little bit more of sort of creative juices, I guess. Right. So actually, I just want to move this. Yeah. So a few notes, sort of, past the, sort of metabolic phases, right? These volatile or gaseous drugs that can be excreted through the lungs. The bile duct travels from the liver to the intestines, containing bile. These are a few just notes that I think you want to take away from the reading. 10 to 15% of drug can be lost just through sweat. Saliva and breast milk, right, are minor pathways for excretion, and I'll show you in just a second. And kidneys are the main route for excretion. So those are some of the bulleted notes I wanted you to take away from some of the reading. Yeah, so these are sort of the relative, routes in which drugs are excreted, and this holds pretty true. I would say for now a long time. So I would go ahead and you just take a peek at this, sort of follow the arrows a little bit, and have a okay understanding of that. I don't think we don't want to ask anything too intense on an exam about it, but just sort of where most let's say drug excretion occurs, for example. Why don't you sort of just be aware of sort of the several different sort of administration strategies, right, for drug delivery. And so some of these in which you'll be familiar with, and I'm probably familiar with most of them, but it's a nice sort of depiction of sort of the options for that. Yeah, something that comes into play as we especially as we get towards conversations about the case studies is going to be these discussions around the therapeutic window, and that's the steady state levels of the drug that remain between the therapeutic and toxic levels. So I'm sure someone in the room has at least a grandma or a grandfather that, like, they're supposed to be taking pills, right? And they take the pills, and then you say, hey, did you take your pills at this time? And they say no. And then you're like, well, that's not good. And then you have to, and then they're like, well, it doesn't really matter, but keeping it in, the therapeutic window is really important. Obviously, we haven't given them enough, let's say, of the drug to get to the toxic level, and obviously they shouldn't take more to compensate, right? But you do want, there's sort of like a, you should take it at sort of the recommended time so that you stay in that therapeutic window, or sometimes it's not effective, right? The other things that'll come in to play definitely are the half-life, right? So time taken for the concentration of the drug in the blood to fall by half. Something to keep in mind. Right, steady state concentration, usually 6 times the drug's half-life. Not particularly important. That's just for your own information. Yeah, formulation ends up being really big, and that's something that I don't think is appreciated by sort of everyone in the world. I think a lot of people, when they take the pill, right, they think that like that whole pill is filled with the drug, right? And I think it's important to keep in mind that sort of the formulation is really important, right? So whether it's administered by mouth or by injection or whatever, right, you have to think about sort of what types of factors that go into sort of that administration. Some of the drugs, right, they taste really bad, right, to take. So they'll sometimes coat them with sort of like a sugary type of coating, right, to make it sort of more enjoyable to take. What a cool area of research that is to get thinking about sort of formulations of drugs. I think that's really, really neat. Yeah, so you guys don't necessarily have to know what the drug delivery systems are, but these are sort of the more popular ones right now. I would say encapsulation into a liposome, sort of another booming area, I would say. Antibody drug conjugates are huge. If any of these really interest you a ton, there's a lot of literature on these. and then link the drug to a synthetic polymer. That also plays a role sort of in the sort of formulation phase of drug discovery. So on that note, that's it. I think we're in just about on time. Not bad. And I'll see you back here on Monday for a discussion about the project. I'd like you all to attend that anyway, because that project's going to affect you either way, and I'll explain. Cool. Thanks, everybody. Have a great weekend.